Hello and welcome back. Um, so I made this video and for some reason it didn't record it. So I already have the screens written up. So I apologize if that means I go a little faster. Um, you can always pause the video and watch. So in this video, I want to talk about cycles, thermodynamic cycles, and their efficiencies. Now I'm using that kind of loosely. It turns out some cycles don't have an efficiency. They have something else called a coefficient of performance, but some way of rating how good a cycle is. So first off, what is a cycle? I'm not talking about motorcycles. A cycle is a sequence of processes that bring a system back to the same or initial state. Here's what I have. I have two cycles drawn here on a PV diagram. So when I say the system starts and finishes in the same state, I mean it has the same pressure, volume, temperature, color, taste, everything. So, so here I have a cycle which takes a system from 1 to 2 to 3 to 4 and then back to 1. And or this one goes from 1 to 4 to 3 to 2 and back to 1. These are two cycles. The difference is the way we sequence through them. Okay. We will look at cycles because we're interested in building machines, and we want machines that can run over and over and over reliably. And that means we want to kind of run them in indefinite loops. We're not looking to make a car out of sticks using sticks of dynamite, a one-time event. We're wanting to be able to run the motor over and over and over. So we look at cycles. There are two main cycles. We have power cycles and, put in parentheses, heat pumps. Oh, sorry. Let's forget that. Heat pump cycles. Okay. So a power cycle is like a car engine or a steam locomotive. It's trying to produce power or produce work. A refrigeration cycle is not trying to achieve work or produce work. It's trying to control heat. We use them to control temperatures, but really the way it works is to control the heat. Okay. So in the case of a power cycle, all power cycles operate between at least two reservoirs, and one of them will be hot and one will be cold. So think of this in a train. The hot reservoir could be the boiler. The cold reservoir could be the air around the train. And what it does is it draws, and the system would be the water in the pipes. So it draws in heat from the boiler, the hot reservoir, produces work to power the train, and then ejects in exhaust or steam or whatever. It cools into the air. So there's always waste, and that's a power cycle. A refrigeration cycle is different. And let's talk about a refrigeration cycle first. For a refrigeration cycle, what you have is the cold reservoir is actually your food, the interior of the refrigerator. The system is the liquid refrigerant in the pipes. And then the hot reservoir actually is, your kitchen, the hot room, the environment. And what it does is it draws heat, sucks it out of the food, dumps it into the fluid, and then eventually ejects it and vents it into the kitchen. That's why your feet get warm underneath your refrigerator door. To make this happen, though, it isn't for free. You have to plug it in. So there's work being added to your cycle. Usually it's electrical work. To say more, let's review the first law. The first law says the changes in the energy in the system for the cycle would have to be Q minus W, as always. However, because it's a cycle, the energy starts and finishes at the same place. So the change in it must be zero. So that tells us that for all cycles, the cycle work must equal the cycle heat. And that immediately lets us determine which diagram went with it which. For a power cycle, you're producing power, so W is positive, consequently Q cycle should be positive. And we can figure out which of these phase diagram pictures, PV diagram pictures, corresponded to a power cycle, because this orientation is the one with a positive area inside my processes. That's a positive area, means power cycle. They always have sort of a clockwise orientation. A refrigeration cycle consumes work, so it has a negative value for work, and consequently a negative value for Q. But what that means is we just go through the stages in a reverse order. A negative area means it is a refrigeration cycle. And there's also an interesting observation. If you took any engine and you were able to somehow reverse it, now in real life that may break your machine, but if you could, it would turn into a refrigerator. Or if you took a refrigerator and you ran it backwards somehow, it would turn into an engine. That's kind of interesting. So how do we compare different cycles? The way we do it is to look at what we want to achieve, to produce, and divide it by what costs money, what we have to input. The simplest maybe is a power cycle. For that, we define something called an efficiency. We're trying to produce work, but the fuel, the heat in, is what costs money. So we divide the work divided by heat in, and that's what we get. You can rewrite this using the fact that for cycle work equals cycle heat. And then, and this is standard here, a lot of times people work with, in these efficiency and coefficient of performance formulas, they work with the absolute values of things. They put the minus signs in by hand. So following that, you can write this as Q in minus Q out, where these are all positive numbers, because the cycle heat would be the net heat. So that's the inputs minus the outputs. I write everything as positive. And then just rearrange these fractions. And if you're really worried about the absolute values and the minus signs, here's a formula where I've kind of made it explicit. So that is a formula for efficiency of a power cycle. So it's interesting. We're trying to produce work, but we're able to express it in terms of heats in and out. It's kind of a neat formula. Notice, because the cycle work has to be positive, that means that Q in is bigger than Q out, which means this fraction is less than 1, and the efficiency must be less than 1. The efficiency cannot be greater than 1, and it cannot be negative either. So the efficiency for a power cycle is going to live between 0, it could be 0 and 1. If it's 0, it's like, a car that doesn't work, it just sits there. So it's not efficient. Refrigerator and heat pumps actually are the same cycle. You just operate it with different goals. For a refrigerator, you're trying to control the cold food. So that means you control the energy or the heat you suck in to keep the temperature cold. Whereas for a heat pump, you're trying to warm up and control the temperature of a warm room. So you can try to control the temperature of the warm reservoir, which means you control Q out. And because you control different things, the way we compare them will be slightly different. But it's always what we want divided by what costs money. So for a coefficient, so to do this, we define what are called coefficients of performance, the COPs. For a refrigerator, it is defined to be, the book calls it beta, and I think that is common in engineering, but I can never remember which coefficient is beta and which one's gamma. Efficiencies are always eta. That's easy for me. But the coefficients of performance, I can never remember. So I always call them COPs. Anyway, for a refrigerator, you want to control Q in, but the electricity costs money. So you do Q in divided by the work of the cycle, and you can rewrite it like this. For the COP, you want to control the heat, the Q out, and again, the work costs money, and you can rewrite that in this form. And with a little bit of thought, then you can see, because the heat for the cycle has to be negative, that means that the net heat is negative, which means Q out is bigger than Q in. And so in this case, we see that this number is, first of all, positive, and secondly, it's kind of obvious from the fraction that it has to be bigger than 1, in fact. So we get the following kind of relationships. For power cycles, we have an efficiency, given by this formula, it's less than 1. For a refrigerator, coefficients of performance, it's given by this formula. And for a heat pump coefficient of performance, you can have this formula, and it will be greater than 1. And for all of them, because they're phrased as a ratio of what you want divided by what costs money, the best engine has the largest possible number. So the largest possible efficiency or largest possible coefficient of performance will give you the best cycle. So hopefully that's helpful. It's kind of a quick review or introduction to cycles. As the course goes through, we will go through in gory detail all sorts of power cycles. And anyways, these are just preliminary ideas to kind of get stuff rolling. All right, catch you next time.